Greetings, ladies and gentlemen. I am Deashan. This is Sulaiman and Lucky Last is Kishor. Today we'll be debating whose fault is it. To identify the main perpetrator of the two-car collision consisting of a Mitsubishi Outlander Aspire with a mass of 1,725 kg and a driver mass of 74 kg. That comes to a total of 1,799 kg. And the second car in that collision was an A3 Audi Sportback with a mass of 1,320 kg and a driver mass of 85 kg, coming to a total of 1,405 kg. Both vehicles are 2021 petrol models, and on the corner of Ballarat Road at Hotley Court, the driver of the Mitsubishi was driving eastward into the city on Ballarat Road. The driver claimed that the Audi suddenly entered the intersection. The Audi driver said he was already in the intersection at a green light and was waiting to turn right onto Ballarat Road. The traffic light had just turned red when the Mitsubishi collided, and the car had not yet crossed the intersection. He claimed that the Mitsubishi driver drove too fast and ignored the green light. However, both drivers were tested for drugs and alcohol and came back clear. Some information from what happened. On the left side of the diagram states that it was a clear sunny day. The Mitsubishi driving along the Ballarat Road, heading towards the city. Along there was a healthy trying to turn right. Both cars collided to each other, which brings them 320 meters away at an angle of 24 degrees from the original crash point. And on the right side shows a diagram of before and after collision. Furthermore, we apply conservation of momentum theory to identify the x direction and the y direction. The equation below is the way to compute to find the x direction and the y direction of the momentum. The x direction represents the direction of the Mitsubishi acting on the horizontal line, and the y direction represents the Audi acting on the vertical line. X direction equals to M1 times by V1 equals to open bracket M1 plus M2 close bracket V times by cos theta. M1 represents the mass of the Mitsubishi times by the velocity of 1 represents the Mitsubishi speed equals to open bracket M1, which is the Mitsubishi plus the mass of the Audi close bracket. Velocity is both cars combined times by cos 24 degrees. And for y direction, we have m2 times by v2 equals to open bracket m1 plus m2 close bracket v1 times by sine theta. M2 represents the Audi's mass times with the velocity of Audi's mass equals to open bracket Mitsubishi's mass plus Audi's mass close bracket velocity of both cars combined times by the sine 24 degrees. By using these equations, it tells the momentum of the x direction and of the Mitsubishi and y direction of Audi. To explain how we calculated it by going to the supplementary materials. From there, we've given the diagram in figure 4. First, in this diagram, we need to
Let's see what happened after the collision. After the collision, two cars collided and went on a motion and come to an end. There was a kinetic energy while they were on the motion. So this kinetic energy came to an end when the car stopped at 3.2 meter. So this change in kinetic friction is work done by the frictional force. The frictional force was working against the mass to bring them to stop. So we can write it into equations as work done by friction is kinetic energy of final minus kinetic energy initial. We can break down this equation as work done by the frictions. We can put it as frictions times displacement is equal to kinetic friction final minus kinetic friction initial. Frictional force can also be break down as minus mu k times normal force times displacement, and that will be equal to change in kinetic energy. We know that the kinetic energy for the final when the car stopped was 0, so we can remove this from the equation and we're left with minus half mv square. And on the other side of the equation, we can break down the normal force into mg, and our equation becomes minus mu k times mg times displacement is equal to minus half mv squared. Now we have m in both sides of the equation and also the negative sign, which we can cancel out, and we're left with mu g delta x and half b squared, and which we can arrange it as b equals square under 2 mu k g delta x. And now putting the value into those numbers, we get b is equal to 2 times 0.7 times 9.8 times 3.t. That's our displacement. And we get velocity is equal to 6.63 meters second. Therefore, after the collision, both the car were sliding at a speed of 6.63 meters second.
I'll be explaining the anti-lock braking system. Anti-lock braking system is a key feature in cars. It helps you stay in control while braking. It stops the wheel from locking up or skidding when you press the brakes hard, so you can keep steering and avoid accidents. As you can see on the right side of the graph, it shows with the anti-lock braking system on top, and the bottom shows without the anti-lock braking system.
Following graph. After the collision, two cars moved in an angle which is not aligned to the horizontal. So this will mean that we have to break down this into two components, that is x component and y component. So let's first see what happens in the x axis. In x axis we can use the conservative momentum law that states initial momentum is equal to final momentum. So for our initial momentum will be the mass of Mitsubishi that was coming along in x-axis and its velocity, whereas final velocity is the mass of two objects times final velocity cos 24 degree. Then again we can rearrange this one to find the velocity of Mitsubishi, and we can rearrange as velocity of Mitsubishi BM equals to mass of two vehicles times final velocity cos 24 degree, and they are divided by mass of Mitsubishi. So putting value to this equation, we get our final velocity, initial velocity for the Mitsubishi 10.8 meters second. This finding says that just before hitting the Audi, Mitsubishi velocity was 10.8 meters second. Let's go to the y-axis now. In y-axis we can do the same. We can, as a conservative momentum law says, initial momentum is equal to final momentum. Our initial momentum in y-axis is Audi, mass of Audi times its velocity, which is equal to final momentum. Final momentum, we have same mass of two object, and the final velocity sine 24. We use sine because it is in the y-axis. So rearranging this for the velocity of unknown, that is, we don't know the velocity of Audi. So velocity of Audi will be the mass of two object times the velocity, final velocity, times sine 24 degree divided by the mass of Audi. So putting values to this equation, we get our velocity of Audi is 6.16 meters second, which will mean that just before crashing, the velocity of Audi was 6.16 meters second. During the inspection, we find out there was a skid mark on the road 10 meters away from the accident, which tells us the Mitsubishi driver hit the brake at that point. Let's find out what was Mitsubishi car driving before that point. So to find out this speed, we can use the work of friction again. So work of friction, which is change in kinetic energy, which is kinetic energy final minus kinetic energy initial. So breaking down this equation, we can get work done by friction, which can break it down as minus mu k times mass times grams, which is its normal force, times delta x, that's a displacement, is equal to half mv square final minus half mv square initial. We have the m on both sides of the equation as a common factor, so which we can cancel it out, and on the other side of the equation we have the half. It's a common factor which we can take as a common factor in the equation. So shortening this down, we get minus mu times gravity g times delta x is equal to half bracket v square final minus v square initial. So breaking down this equation furthermore, we can multiply 2 in both sides and we get 2 mu times g times delta x equals, the half get cancelled with the multiplication of 2 and we are left with b square final minus b square initial, which we can break down again to minus 2 mu g delta x minus b square final equals minus b square initial. We have the minus in both sides of the equation here again, which we can cancel it out and we get v initial as square root of 2 mu g delta x plus v final square. Putting value to these unknowns, we have only one unknown left, that is b initial, and we get our b initial after putting the values to those numbers, we get initial B is equal to 15.93 meters second, which we can convert it into kilometer per hour. That will be 57.3 kilometer per hour, which will mean that the speed of Mitsubishi initially was 57.3 kilometer per hour. So
Conclusion, the speed of the Audi was 22 kilometers per hour, and the Mitsubishi speed at arrival was 57 kilometers per hour, which was reduced to 39 kilometers after braking. The Barra Road allocated speed limit is 60 kilometers per hour, therefore proving that the Mitsubishi was not speeding and that the Audi was not stationary, causing the accident to occur.